For today, I am bringing this topic, optimizing hydrogen fabrication for aortic valve replacement. In the US, at Rice University in Houston, Texas. Maybe you know Houston a little bit more for the NASA. I visited the NASA as well. At that university, I was developing aortic valves. Uh, I am going to talk why specifically aortic valves. But sometimes to design this kind of medical devices is complicated, and I'm gonna teach you how to do it, just changing one mechanical parameter. I did this research with Jane Van Allen. She was my PI, my principal investigator. She is an extremely expert and highly respected scientist in the field of the biomechanics of the current. So let me see how can I move between slides. Yeah. So what is important to study this topic? Well, mechanical valves are not viable options for pediatric patients. Something that happens frequently, not just in Ecuador, in general in South America, many babies born with a defect in the heart. Sometimes this defect uh, we need to replace a specific part of the heart. In this case, the aortic valve. However, we have different kinds of devices, medical devices, like different kinds of aortic valves that we can replace. One of them is a mechanical one, but one problem that we have with the mechanical valve is the baby is going to need a different aortic valve, different ages. So it's not a really good option since this baby is going to take a lot of surgeries during his or her life. So we are trying to find another alternative to make this kind of device, the aortic valve. So one option is developing tissue engineering per valve. What is the meaning of tissue engineering? Is instead of fabricate something with plastic, with polymers, with metals, instead of that, we're trying to replicate the same kind of tissue that we can find in the plant. So how is this process? You have a disease in valves, for example, with stenosis. I don't know if you're familiar what is the meaning of stenosis. Stenosis is a disease when the tissue of the leaflet become stiffer. Why is this happening? Sometimes because you're eating so many lipids for so many reasons. But when this happens, you need a replacement. And what is the process with a tissue engineering aortic valve? You need to create the scaffold. And after you create this scaffold, it could be like a polymer, it could be a plastic. I am going to talk about what specific kind of material you can use for this. But after you create this scaffold, you need to put cells or sealing cells on this scaffold. And after these cells proliferate and replace the scaffold and create the tissue. So it sounds like a little easy in general, but just try to replicate the same characteristic, the same kind of mechanical characteristic of the scaffold is extremely complicated. So I'm going to teach you how to do it just the development of the scaffold. And maybe in the future, in different kind of presentation, we can talk a little bit more about talk a little bit more about how to do cell culture. So, well, in the combination of these two steps, you can do the tissue engineering per valve. Um, so, why? How do you choose the kind of scaffold that you need to put the cells? There are many different kind of hydrogens. I don't know if you're familiar with hydrogens. I'm gonna explain a little bit more about what is hydrogen. Basically, this kind of component is the matrix. It tries to replicate the extracellular matrix of the tissue where the cells are going to proliferate. And we have different kind of hydrogens. We have natural hydrogens like collagen. We have synthetic hydrogens. And for this specific research, I use PECDA. PECDA is really useful because it's approved by the Federal Drug Administration. so it is safe to use in the human body. And what is serious for us is we can use this kind of synthetic energy. First, it is like compatibility, which means that it is not going to hurt our body. We can change the mechanical properties. We can change the parameter, like for example, in this case, the ultraviolet exposure, and we can increase or decrease the stiffness of this hydrogel. Well, we can have a couple other parameters that I'm not going to talk for the time right now, but an hydrogel basically is a formula that you can change this hydrogel. In the body, it's gonna be hydrated by the blood, but when you're designing the scaffold, you can hydrate them with PDAs or water in general. So, as I mentioned, the first part of this creation of the Aortic valves, you need to create a mechanical design that duplicates the extracellular reagents. So before to do that, you need to understand a little bit more about what is the behavior of this kind of material. In this case, the aortic valve. So we know many of you are biomedical engineer or maybe are different kind of engineering, but you're really interested in this field. So for this people who are not biomedical, I'm going to explain a little bit about what is the behavior of the start. Just looking at the point of the aortic valve. So the main purpose of the balance in the stomach is to keep the direction of blood flow. So I'm not going to talk about the cardiac cycle, but more or less when there is a difference between pressure in one side, in the one open side of the heart, and there is a lower pressure in the lower part of the heart, there is a field because the flux moves between higher pressure to lower pressure. And this kind of mechanical parameter open the valves. And what is this important to study the aortic valve because it's connected with the aorta. And what is this important? Because basically that is the main pump that we have in our body. And as well for that reason, because the aortic valve contains a lot of stresses, is used on that in a specific age. If you have back health, and a good this kind of living, maybe you're gonna need this kind of replacement. So this thing I just wanna that you keep in your mind that the main mechanical parameter that open the the bounds is the difference in the gradient of the pressure. So as you can see here, this is the general movement of the blood flow during the heart beating. So now that you understand like the main kind of movement that you can find in the sword that I just want to that you keep in your mind that the bounds open because of the differences of the texture. Now we need to understand the material. How is the composition of the tissue of the plant? So I'm not going to be extremely specific. I just want to you keep in your mind that there are three layers. The first layer, the ventricular layer, the spongiosal layer, and the fibrosal layer. And you have different kind of cells, the big cells and the back cells. So what is the main purpose of each kind of composition layer of this tissue? The ventricularis has live elastin. As the name says, elastin, the main purpose is to provide flexibility to the tissue. The Spongiosa has a lot of protein glycans and glycans and glycans. We don't want to be extremely specific about that. These kind of cells are extremely useful for the decay of the heart and other kinds of tissues. I just want to focus in the ventricularis and the fibrosa. The fibrosis has a lot of collagen. What is the collagen? Why the human body is mainly made by collagen? Why is this important? Because collagen provides structure, so it is stiffer than the elastin. So right now, just like I know it, we put three different kind of layers in the front, and with that one layer to provide flexibility to the tissue. We have a third layer which provide a structure like a building for the hair. So with this, it is important to realize that you have a material that is extremely complicated if you analyze the composition way because it has a lot of flexibility and it has to be stiff the same way. So now that we understand how is the distribution of the tissue in the part, and as well we understand what is the mechanical parameter that facilitate this movement of the hand. Now we need to understand how the stresses will be distributed to the in the tissue. So, I don't want to be as well here specific. I don't want to be specific with the terminology, but we have these two kind of stresses in the part. We have the circumferential and we have the radial. As you see, the circumferential surrounds the leaflet, and the radial distributes from the center to the outside part of the leaflet. So the superficial stress quantified the stiff will be the result part, will be the tissue. And the radial stresses try to quantify the flexibility of the leaflet of the aortic valve. Um, so basically, in the radial direction, you have a radial sting, and in the circumferential region, you have a lot of collagen 1 and 2, which is this type of collagen are the most common in the human body. And this is a real leaflet that we got in the laboratory. So from this, we can at least start to do the mechanical design of the scaffold because we understand that our material seems to be flexible and it has to be firm at the same time, but in a specific region, in a specific distributions. As well, we understand what is the main kind of parameter that opens the outbound, the defines the pressure. So with this kind of with this process, we can be sure about how we can start to modulate the scaffold. So we need to take into account the rigidity, the flexibility, and the anisotropic behavior that we can find in this kind of tissue. What is the meaning of anisotropy? Maybe if you're mechanical engineers or maybe you're material engineers, you know that the properties, the distribution of the properties is not the same in all the directions. If you calculate an material that has anisotropy, it means that the distribution of the properties are different in different directions, which means that it is extremely difficult to modulate that. So, something that I want to highlight as well too, in the when the leaflet open, when the rotating band open, you can see how is the distribution of the elastin, the elastin that relax. Um, and after, when it is open, when the valve open, the last thing is stretch a little bit. Right? You see some of the collagen which is in brown, in the brown line, you can see this range in the leaflet. And this provides the stiffness, the structure of the leaflet when you have when the fluid is flowing in the aortic valve. So for this, we can understand that for the material that we're going to design, we need two things. We need something that combines flexibility with rigidity, and we need to understand that one part is more flexible and one part is a little bit stronger than the other. So some people are under this kind of combinations when you're designing the scaffold for the teaching of the output math. Yes, I always mention that you need to start in the most basic way. After you can increase a little bit more the difficulty. So, the way you start this is combining two hydrogens with different molecular weight. One hydrogen with 3.4 kilodaltons, I think that is the unit, and another hydrogen that is less stiff, less is a little bit is softer, with 6 kilodaltons. It, maybe this is a little tricky. When you increase the molecular weight, you reduce the stiffness. And after you need to combine these two kind of hydrogens with an interface, and because as you saw in the Aortic valve, uh, you can combinations between the radial stresses, the circumferential stresses. So you need to combine both hydrogens with one part with more stiffness and another part with less stiffness. And in this case, the combination was with a flat interface. And why did we did this? Because I was trying in the beginning to figure out how to do this initial behavior. Um, and this is the hydrogen. This is the fruit of the hydrogen. But when I also know the shape of this hydrogen, as you see, this has this ball shape. As a biomedical mechanical engineer, you know that this ball shape is useful when you apply mechanical testing, like a function testing, when you need to be sure that the material is going to break exactly in the middle of this ball shape of hydrogen. So, we have a couple of strategies to modulating the mechanical characteristic of this hydrogel. Right now, I just want to highlight, right now, what I do is the hydrogen becomes one part of the other. Um, and why is this important? Because as you saw in the leaflet, one part has a lot of elastin, which means that it has a lot of flexibility, and the other part has the ontology, which means that is a little bit it's um, so the different kind of ways that we want to control these mechanical characteristic of the hydrogen, and you can make a reinforcement sorry, with natural synthetic fibers, like a composite material. You can change the cosmetic procedure, or you can play a little bit with the geometry. Um, for the time that we to this presentation, I'm going to talk about how you can manipulate the mechanical property of this composite hydrogen, just changing the transmission procedure. So, I in this project I had two A's. The first A was to determine what is the optimal UV energy dosage to try to increase and decrease the young modulus. As you know, the young modulus quantify the stiffness of the material, how soft or how firm is the material. So I want to try to quantify if I expose this hydrogen to less more UV light, if this is going to increase or decrease the behavior, the mechanical behavior of the hydrogen. Because we need to, what is the main idea? Just to remember, the main idea is to manage the same mechanical behavior of the extracellular matrix. So we need to like try to control and try to match the behavior of the extracellular matrix with the behavior of your current material, which is in this case hydrogen. Because after that, the cells are going to proliferate and the hydrogen is going to disappear. That is the main idea. And the second, as you know, maybe some materials has a more linear relationship, which is more difficult to characterize this kind of material. So my question was as well, what kind of the strengths and the strain behavior I'm gonna see in this kind of composite material? I'm trying to mimic the same behavior of the extracellular matrix of the tissue. So these are the two A's, and I want to say that as well, like as I mentioned, if you're biomedical, if you're mechanical, maybe you're used to or you're familiar with big machines, bigger machines, like machines for metals, machines for ceramics, machines for polymers. But when you're trying to characterize the mechanical behavior of the tissue, you need a special machines. And these special machines, this is an example. First, you can change the velocity, this signal, and as well, this not is like it's difficult to explain, but this not signal is so many forms that you're putting to try to move the head of the machine. So and as well, you need to put all of this the sort of a weather type. It try to replicate the same environment on the tissue. So is let me know if in the universities that you're in right now, if you find this kind of material. In Ecuador, I haven't seen them until now, like a mechanical machine exactly for tissue. I know that it's extremely expensive, but in the US, it's pretty common. All of the universities at least have one. Um, so I just want to try the mechanical tester. This is like a zoom of how is the machine when you put the hydrogen. The putting the hydrogen as well is a little bit tricky because the material is a polymer, so it's a little difficult to handle because these units maybe are going to break the material. And maybe you're creating more concentration, stress concentration in this part of the material. And as you see, maybe if you're familiar with mechanical testing, this is completely different when you're working with metals or when you're working with ceramics. And the machine that I was using for providing the UV light, maybe I didn't explain this, but really important the UV light because you need to translate the PDA, the material, because the PDA is a liquid and you need to translate, which means like the polymers, the polymer change and create this solid behavior of the polymer. So what is using for providing this UV light I was using this flash machine. Um, More or less, if you have physics class, that the wavelength of the UV light is between three, 350 and 700 nanometers. More or less is that you have like a range. 1.6 per flash and you have 10 flashes per second. So something in this thing, you didn't say how it was quantifying how many energy I was providing to the hydrogen was using these the unit was the joules and it was in concordance with the number of flashes that I can provide per second. And as I mentioned, I'm gonna explain better so you can create the hydrogen, but it is want to line that you need to create these models because the technology is a founder. And after this founder, you put with a couple others liquids, and it's not going to be bakery. You make the cakes, you make the milk, you make a lot of things, and then you put all of that in a bowl and after you mix all of that, it's not necessary. You need to put the PGA, you need to put a couple of other things in a mold. And after that, you put this mold into the plasma machine and you control in that way with the machine how many flashes and in that way how many energy will you provide into to this material. So you do the hydrogen job. As I mentioned, you find the PTA, which is a polymer, and is polymer. You find an Hidrogel. Hidrogel is a foreign initiator. Once a foreign initiator is something that is activated with UV light. When you find into pure water, it's not water, but with a little bit extra purification process. Someone who is familiar with chemistry or something like biological thing, maybe has this kind of machine for doing the ultra pure water. So you mix is in a tube, and after you apply UV light, You apply this UV lamp to the tool, which is inside of the machine, and you create a composite hydrogel with a specific young modulus. Remember that the young modulus is how or how soft is the material. That's a general process. So what I was doing exactly with the models that I mentioned before is put the composition in one side of the mold, apply a specific amount of amount, and after I put in the other side, sorry, on the other side, the composition, and I play another time, another amount, sorry, of UV light flashes. With this, you can create that composite hydrogen, which one part is going to be stiffer than the other, because remembering that the leaflet, the updated amount, has one region which is the listing region, which is more flexible than the other. And the other is important for provide this structure from the leaflet. So this is the combination, the characteristic experiment that I did. Was combining between two kinds of flexion because you need at least 100 flashes because of the the more or less you can if you already took physics, 100 joules is more or less the minimum for making this transition procedure. So it's like playing with this kind of combination between 200, 500, 300, 500. We have a lot of combinations to see what is if this purpose of material is going to increase or decrease the levels. And um, something that is really important since you are engineers and understand that one of your engineers is how are you what is your plan for the data processing? So in the when you're working with mechanical parameters, in general, with all the parameters, you're gonna have noise, and you need to reduce this noise. You need to apply a filtering for this noise. One technique for applying this kind of reducing the noise, specifically for tissue analysis, is the Hansen filter. And people know about how you can use this equation. I mean, right now you can change the but it's important that you at least understand the general way that you can choose one filter instead of another. In this specific case, the Gaussian filter is the most common one when you're doing mechanical testing for tissues. And I did this in Python, so you can just read the library in Python. And this one, the filter is the signal of the mechanical tester. And as well, it is important that sometimes, as you're going to see, you have your brains, and your brains maybe have a very non-linear behavior. Uh, in general, something that is non-linear is extremely complicated. Maybe you're familiar with the Navier stocks. I understand about that. What is difficult about solving that system of equation, the Navier stock for fluid mechanics, is the non-linearity that it has. When something when you find a differential equation with this non-linear, I am sure that you really do differential equations. You need to try or you try to linearize that. So when you're working with polymers, it's very common that you're gonna find a curve that is non-linear. So in order to manage your mathematical modeling with the raw data, you need to do this method of curve fitting. In this specific process, I was using this numerical method that until now I have no idea how to pronounce, but we were using a software called Genius. If you need to do numerical methods, maybe you are not really good in programming, I strongly suggest you that you can use Genius because Genius is a little easier environment to work with numerical methods. So I'm going to show you right now the results of the discussion of the project. This is the raw data in blank, and in red you have the data after they apply the filter. So in this case, something that was really amazing, and maybe it's important to explain again what is the meaning of this graph. The y-axis is the stress, and what I used for the stress was since this was an initial study, I was using the classic definition of stress. You have different definition of stress, but when you're doing like um, experiment that is just an it has in the early stage. It is important to apply or is a suggestion to start with this more basic definition of the stress. It is forms over the initial area. It has a specific name. The name is Fiona Kirchhoff. When you are using the initial area, maybe you're familiar with is the difference between Kochi and Fiona Kirchhoff stresses. This is the Fiona Kirchhoff, so that is the stress that you're seeing in this white line of the image. And in the x-axis, you have the speed, which is the speed is just the change in the length over the original or initial length. I'm not sure that you're familiar with this. Maybe I just want to overview this. So as you see, when you apply more stress, more force to the hydrogen, it is increasing it length. But it was really easy to see that the relationship on 4 years longer was a linear relationship. And as well, we did a combination process of the machine. So I got almost nothing noise on my signal. And this is what I mentioned in the first meeting because the dotted line is the cure fitting uh, strength, and the wrong in continuous line, not line, is the raw data. So if you see the raw data, it's not with not enough. There's a second thing which non-linear behavior. And I was realizing this behavior because after it is important because if you quantify the young modulus is the slope of the strain of the stress. So it is important to have like a linear theory of your data if you want to try to quantify the young modulus. So like I mentioned, this kind of pure theory that I was doing, I did it with GeniusPod, which is a extremely useful software that you can apply. So with this in mind, I just want to say now, if I increase the number of fluxes, I was increasing the slope, which means that I was increasing the volumes. And the main idea is trying to increase until you have the same young volumes of the extracellular matrix uh, in your hydrogen. So usually when I was starting with 200 flashes and I was reducing the number of flashes, I was reducing the zone, which means that it was forming my hypothesis. One way that you can control the mechanical behavior of the underground of the sample in the output is just changing the amount of human light that you need to provide to this flash. And I want to highlight that if you increase so much with UV light, you can see that there is no like a huge change between the lines. So what I am telling you this, it means that you cannot just apply so many energy to the nitrogen. It means that there is an optimal amount of function that you can provide without compromise the mechanical behavior of the antibody. So that was basically the experiment. The experiment was trying to determine which is the optimal amount of flashes in the amount of energy that I can provide to this tissue, to this nitrogen. So I can have an optimum values, which is an optimal modulus when I compare with a normal tissue, with a normal extracellular matrix. Um, This point is just to illustrate is with numbers, more or less, what is the young modulus of the tissue, and as well as the young modulus of the hydrogen is in the order of or stuff. And as you can see, when you increase the number of flashes, you can increase the young modulus considerably. And as well, you can increase the young tensile strength. But, something that is important to keep in mind, maybe the strength, the flexibility is not going to change so much. It's more or less the same. So now, like all of this, I want to go to the next part of this experiment. So with that experiment, I already know what is the optimal amount of energy that I can deliver to the antigen in order to match the same young molecules that you're going to have in the future or in the extracellular matrix. So with that, you created a good environment. So the cells, when you put cells on the hydrogel, is going to proliferate appropriately. And I think it's important to characterize in this part the in the way that the hydrogen break when you apply pellets. So it is important to realize that this kind of material is going to be ductile in kind of other materials can be brittle. But this specific material has both behaviors. Sometimes you have a more brittle behavior. Sometimes you have a more ductile material. So what I mentioned is I want to find that it's really difficult to try to manage the real behavior of the tissue with of tissue engineering material with the tech DA. So I just want to find out this exactly. Sometimes you have a brittle materials, new behaviors, sometimes you have a ductile behavior. So one risk that you have when you're working with aortic valves is although you're trying to mimic the same behavior of the tissue, maybe you don't have the full control because the material sometimes behaves in a more brilliant way or sometimes behaves in a more ductile way. So we now have a lot of challenges in this field of engineering. We control just a specific point, but until now we don't have or we are not sure how we can control other aspects of the material so we can exactly mimic the behavior of the tissue. So the conclusion of this is there is a specific amount of flash dosages that you can provide to this material. Once given this 200 joules, between 200 and 500 joules, that you can increase in an optimal way the young values. And something that I was looking at as well is this strength behavior is linear. Although it is composite, the behavior is linear. With it is really helpful to know this because in the moment that you're designing or in the moment that you're doing simulation, you can see this as linear. And um, before the hydrogen shows more ductile behavior, you can see a little bit of radial behavior as well. So we cannot be sure about if our creation of working groups is going to behave exactly as we are modeling. There is the that with this experiment, it is important that we can control, at least in one way, the stiffness of the hydrogen and mimics the extracellular matrix. And with this kind of control in the environment, when we put cells that I learned how to do this cell culture in New York, uh, we put cells. It is on this presentation in the matrices after we put cells. And since we were able to control the mechanical properties of the sample, the cell proliferates and replace the sample really, really well. So I just wanted to know that if you want to work in this case of the field, The most important point is create a good scaffold controlling exactly as well, as much as you can the mechanical properties, because after the same part is a little bit easier. You just need to put control the environment, control the proliferation, put in the incubator. But the critical part is create a really good scaffold. So I know that I just have 45 minutes. So thanks much for your attention. If you want to still in contact, this is my social media, the Instagram or personal LinkedIn. If you're interested in tissue engineering, I really want to connect that with people from biotechnology, bioinstrumentation, biomaterials, because this field of biomedical engineering or bioengineering is so huge, and it is impossible to just address the challenges that we have in the healthcare system using the way. So I really want to connect many people with other kinds of parts of the bioengineering. Well, thanks so much for your attention. If you have any question, I am happy to answer it.
Yes, yes. Thanks for your presentations. No?
Yeah, it was a pleasure.
Okay, yes. Have only questions. The one question is how does UV light exposure time specifically affects the mechanical properties of the hydrogels, such as Jones modulus? Right?
Yeah. Okay. Well, it's something that maybe the answer, I'm gonna try to explain that if I have like a central vision thing, is gonna be easier to explain, but recently I don't have. But basically, the polymer change are going to combine with this kind of UV dosage thing. So if you have a, imagine that this is the polymer change, my hands are the polymer change. So when you apply the more or less UV light, you're gonna like manage more or less the polymer change of the hydrogen. So in that way, imagine that these are the polymer change. It's gonna be like elusive or far away when you apply more or less UV light. So basically, when you apply more UV light and open a UV light, the polymer change is gonna be closer, and this will create a more resistant or a more strong material. You don't want to be like a extremely strong material, because remember that the leaflet has to be flexible at the same time, because it has to open, because basically the optimal ways in this way. So uh, maybe I don't know if the question is like the chemical way. Maybe I'm not fully able to explain in the chemical way, but basically, the juvenile control, how close or how far is going to be the polymer change of the between them. In that way, you can have a more stiffer material or more soft material. I think that I can explain maybe with a visual explanation is going to be easy, but for the person who finds the question, I'm happy to send like a more clear images that explain that, because I didn't put that in my slide. I thought that I answered the question.
Oh, okay, thanks. The other question say, what challenge exists when trying to replicate the anisotropy of collagen and elastin in a scaffold?
The misotropy, how difficult is to modulating? That was the question. How difficult is to introduce the misotropy in the hydrogel?
Oh, yes, the anisotropy of the collagen or maybe the elastin in the scaffold.
Okay, I'm not listening very well the last year, but more or less I got the question. Uh, People introduce this American misotropy. It's extremely complicated to introduce an misotropy. One way is trying to introduce on purpose different arrangement of the stiffness of the material. In my case, what I did was try to combine a stiffer hydrogen with a softer hydrogen. So in that way, when you apply the load is going to distribute in a like randomly way, which is more or less an isotropy. Another way to introduce recipe in the algorithm is with fibers. With fibers, you can align the fiber like in inclined way, or you can introduce fibers in vertical way and in horizontal ways. In that way as well, the distribution of the element is going to be a little bit randomly. But what is the main problem of the isotropy is the is that. So in general, but sadly, the teacher concept and necessity behavior. So something that is really useful to like analyze the anisotropy or to introduce the anisotropy is with simulation. Here we talk about that the simulation with finite element analysis. I am not sure how uh, familiar with you with finite element analysis. Maybe you use ANSYS, maybe you use an OpenFOAM, maybe you use the solver of the SolidWorks. But to treat analyze the isotropy, instead of doing experimentally, usually you try to do it with a simulation. So in summary, how do you introduce isotropy in the animal is combining with two different kind of languages with different molecular weights, or with fibers of other material inside of the hydrogen in different directions, or like virtually, you can introduce this anisotropy using the finite element analysis method. That is the way that you can do it. I don't know if you have any other questions. So you can answer in Spanish. I don't have any problem with that. I did this presentation in English because I was speaking so many Spanish in my country. So maybe it's a good idea to practice a little bit. So I don't know. Some of you have questions. So if you're doing it in Spanish, it's perfect.
Ah, ok, no worry. A ver, los presentes si tienen alguna pregunta también en toda la ponencia, lo pueden explicarlo de forma español también, no hay ningún problema.
Creo que Rani quiere preguntar algo.
Oh yes, but I feel comfortable with English if you don't
Yeah.
mind.
Yeah, sure.
All right. So you mentioned that this behavior might support, and the conclusions, I guess, it was that it might support cell growth and ECM formation. So
Mhm.
my question was, have you ever performed, or are you planning to perform any in vitro tests with cells to validate
Yeah.
this potential?
Yeah, I'm gonna do that before we begin. One of the use okay, in the beginning, exactly it was because it's a federal government administration approved. So that is a huge advantage because if not, you could first try to create a material and after send that to the FDA, and maybe the FDA is going to take like 5, 6 years to approve that material. So for that reason, I use FDA because my next plan is used in vitro process. Something here in Ecuador, the disease engineering part is not well developed. Maybe I didn't mention that, but when I got the Fulbright scholarship. Part of the scholarship is that you need to come back to your country and try to develop the area that you study in the US. So something here in Ecuador, we don't have like so many machines to perform this in vitro. Then, fortunately, I got we got food. The food is the farm where you with maybe or something like this. The food is the farm where you're working with the cells in a sterilized place with the sterilization place. So we got as well cells from porcines from pigs, and now as well as have an incubator, so we can go to the next step, which is the in vitro part. But it's not gonna be a really good experiment because the machine is like a really it's not simply machine. It was difficult to find it. But in the future, in the following year, I'm coming back to the US. So hopefully I can do a more advanced in vitro experiment. But something here, I just can go, I can just reach until really specific part in the in vitro process. I got the cells from the pig. Why I'm using cells on the pigs? Because the shark pig and the human pig is more or less the same. And hopefully, as well, in collaboration with the Faculty of Medicine here in Ecuador, I am having a little bit access with real humans body. which maybe I can got like real cells of the fur of the human hair. But the next step for sure is the in vitro part. I am struggling a little bit with the machines, as many of South American and Latin American countries are. And as well to getting the cells is quite difficult. Many of the pixels, but it's going to be useful, really useful to have real human cells. But here in Ecuador, that's quite complicated, even for people who is studying medicine. So yeah, my next step is doing the in vitro. Sadly, I am struggling with the machines and getting the cells for doing the in vitro tests.
Okay, that's really interesting. I was also interested in the part of the UV based crosslink. Is this your personal idea, your personal like research to use this UV based crosslink strategy, or it is from anyone? And my question specifically was that if this could be applied to other type of tissues, like vascular grafts, or I don't know, like cartilage.
Yeah, well, in the first part, I think there was two questions. The first question, yes, it was my idea. Where I discovered that some people sometimes as engineers try to do the most difficult way to resolve something. Many engineers there in the US try to like change the geometry, make another reinforcement with different kind of fibers. And it really increase a little bit of the young models, but when I was doing the process, I realized that this qualification procedure is a key part when we're doing the. And nobody before me, nobody in my laboratory, nobody in general in the US, but in my laboratory, nobody tried to replicate this before or tried to do this before. So this idea, she got this idea in the way that many people learn, try to learn the protocol, mm, as much as you can fail constantly. And in that moment, I realized that maybe just changing these little parameters is going to decrease a lot the young models and hypothesis was correct. The second point, yes, you can transfer this to other kind of tissue. What is the main problem? I think is getting the cells that you need. For example, my last semester in the US, I was working with three cells, which are the main cells that you have in your lungs. I was working with two cells, which those cells are present in your intestine. So getting those cells in the unit was really easy, honestly. Like I just need to follow and you're gonna get it. The process you can transfer to all other tissue, but getting the cells maybe is gonna be difficult. First, for the pulse, and second, for example, for the animal, you can for the third you can get it from the pigs, right? From the intestine and from the lungs. And then we found like animals which whose tissues more or less replicate the same behavior and the same size of the human body. So in theory, yes, it was my idea the UV light dosage. Um, and secondly, you can transfer this method to other tissues, but the main difficulty that you're going to face is the way that you find the cells, because I don't know in the US is quite easy, but here in South America or in Latin America, maybe the importation costs are extremely expensive. And as well, you need this fridge time to get these kind of cells. But you can transfer at least the process, but I'm not sure if you're gonna get the cells. So that is my answer. And thank you so much, Raymond, for asking that. I don't know if anyone else has another question. Is English? You can ask in Spanish. Yo no tengo ningún problema. Todos hablamos de español, pero la bioingeniería en general se hace en inglés. No, pero después preguntas. Bueno, fue un sí,
¿No?
sí.
Hola, ¿sí se me escucha?
Sí, te escucho, Carla.
Ah, ya. ¿Cómo, o sea, no me quedó muy claro cómo es que se puede asegurar la biocompatibilidad a largo plazo del hidrogel cuando pues se implanta el sistema cardiovascular?
Ya, ¿cómo se asegura la compatibilidad? Esa es la pregunta, ¿no es cierto? De que no tengas una coagulación, por ejemplo.
Claro.
¿Sí? ¿Sí escucho bien? Porque te escucho con un poco de eco yo. Ya. Entonces, ¿cómo se asegura? Básicamente, el problema con las válvulas prostáticas, con las válvulas mecánicas, es que la persona que la toma va a necesitar anticoagulantes toda la vida. En cambio, con la válvula de ingeniería del tejido, básicamente tú creas una matriz. Esta matriz es un material biocompatible y biodegradable. Y obviamente ya pasó por todas las pruebas de citotoxicidad. Entonces, una vez que tú pones las células en la matriz, estas células empiezan a sensir el ambiente de la matriz, si tiene más dureza o menos dureza, y en base a eso, las células empiezan a proliferar. Y esta proliferación posteriormente va creando tejido. Y este tejido en final viene replicando al mismo tejido que tú, digamos, en teoría tendrías. Entonces, el proceso de que no necesites anticoagulantes o que se asegure la permanencia es mediante la proliferación de las propias células que componen el tejido. Actualmente no se conseguimos llegar a una válvula totalmente por ingeniería de tejido, por las razones que les mencioné en la presentación. Pero si ustedes van a empresas como Stryker, como Medtronic, como Abbott, van a ver que actualmente sí hay válvulas que tienen una partecita que combinan tejido, ingeniería de tejido, junto con otra partecita que tiene la parte de la válvula mecánica, como que los leaflets le dan con este proceso. Pero, como te mencioné, todavía hay muchísimo que explorar y la ventaja de que no, el cuerpo no te rechace esta válvula es porque estás introduciendo primero células que en teoría tu propio cuerpo produce. Entonces, no podría existir este proceso de rechazo, pero aún falta mucho para llegar a una válvula completamente reemplazable. Muchas gracias, Carla, por tu pregunta. No sé si la respondí.
Sí, muchas gracias. No me sé si existe otra pregunta. Have anyone question? No? Okay. Well, thank you so much for your presentation, Mr. Esteban. We really appreciate the time, knowledge, and you shared with us today. Really.
Yeah, well, it was a pleasure. And if you have any other event or you wanted to, I am mechanical engineer who falls in love with biomedical with my social media. And thank you so much, everyone, for your attention. So see you later, and thank you so much.
Okay, nice. See you later. Bye.